Philip Hackney from the University of Louisiana at Lafayette is going to be presenting. So thank you very much for joining the topology seminar at Kent University. So the title of his talk is Partial Groups and Symmetric Simplicial Sets. Okay, Philip, please take it away.
Yeah, well, thanks for having me. It's great to be here, although I guess I'm just here virtually. Yeah, so today I want to talk about what's in the title. Maybe there's supposed to be a simplicial between symmetric and sets, and it didn't make it onto the title slide. So this is mostly based on a preprint with Justin Lynd, who's my colleague here, and I'll say a little bit more about that, but not all of it. Yeah, well, why don't we get started? So I want to start with a theorem that, the farthest I've seen it back is in Grothendieck's work, which says that if I have a simplicial set, then it's a category just when these so-called Segal maps give us a bijection for each n greater than or equal to 2. So what this is saying is that an n simplex in a category is actually just a string of one simplices. Okay, so we think about it as these one simplices. These are the morphisms in the category. And what is an nerve of a category? Well, it has n simplices, composable strings of morphisms, like so. So I've written like particular formulas down for this. It isn't so important. This is how n simplices in the category look. And what we should think about is, I'll just draw a couple pictures of these. So here's what a 2 simplex looks like. So this is a pair of 2 morphisms, which could be composed in the category. But of course, I can sort of uniquely fill this in to a 2 simplex. There's another face here that I haven't drawn in, and that's exactly the composite. So this isn't giving me all the data, but I can recover it from the other face of my simplex. And of course, this also tells us something about associativity. This information is giving us, saying we're starting with F1, F2, F3. And there's sort of 2 ways that I can start filling this in. I could first fill in this back face and then compose along this bottom face. And that gives us something like, first compose F2 and F3 and then compose with F1, or I could fill in this front face and then this other front face, and that gives me the other associator, and they end up being the same because this comes from a simplex. So the nerve is a fully faithful embedding. So I find myself often thinking about categories just as certain simplicial sets. And moreover, this inclusion has a left adjoint. So small categories is a reflective subcategory of simplicial sets. And this is sort of done by sort of looking at the one skeleton of your simplicial set, taking the free category on this, and then imposing some relations coming from the 2 simplices. That's how you get this reflector. So I want to talk about another simplicial set. So this comes from a partial monoid. So we've got partial groups in the title. Partial monoid seems a reasonable thing to have in the title or in the talk. And what is this? So this is a set together with a partially defined multiplication, which I'm going to write as dots, so that it has a unit. There's something that multiplies with everything and behaves as an identity element should. And it satisfies sort of a strong form of associativity, so that if x dot y and x dot y dot z is defined, then so is the other way of associating it. And they happen to be equal, or vice versa. And one thing to note is that this being defined actually is implying y dot z is being defined as well. So we can form a simplicial set out of this, just like we do with regular monoid or a category, by letting the k simplices be the length k multipliable words. So these are the ones where there's some parenthesization where I can actually multiply them together, which by this sort of strong associativity means that for all parenthesizations, I can multiply them together. So a theorem of Bergner, Asorno, Azarova, Ravelli, and Scheinbauer says that this is a two-Segal space. So it's not a nerve of a category because I can't multiply anything that I see. But it satisfies something that you may have heard about from Walker, I'm not sure, which is this two-Segal condition. And I don't want to spend too much time on this, but these are simplicial sets, so that these sort of squares that look like this happen to be pullback squares. So it's kind of pullbacks of outer faces along inner faces is what you have in a two-Segal set. Right. So this is sort of some background. And I've been thinking about these two-Segal spaces for some time, maybe quite a bit, since 2020 or so. And over here at UL Lafayette in spring 2022, my collaborator Justin was he was giving a working seminar for the grad students and other faculty in algebra, which was all about this notion of partial groups. And I wasn't at this seminar. I don't know if I knew that it was going on or I didn't know that it was going on, but I was hearing about it here and there, and there were some other algebra seminars that were about this. So this is me down here thinking about this. So I knew the stuff on the previous slide. So partial monoids are two-Segal sets. And I'm like, well, what is this partial group business? And yeah, so I was curious. I was curious what this was about. And I asked Justin, and I said, oh, so what are these partial groups, and are they two-Segal spaces? Seems very reasonable thing. And we chatted about it on my porch, and eventually I learned what these are. So I'll tell you about what they are. So I haven't said anything about that yet. They're not partial monoids. So I want to say something about inverses and partial monoids. So the thing is if an element in a partial monoid has an inverse, meaning something that I can multiply on both sides and get the identity, then it actually multiplies with everything. So this is a calculation. So I know that 1 multiplies with everything. So 1 dot y is defined. This is just copying in from above. That is x inverse dot x dot y. But then because we have this very strong form of associativity, I can move these, and this is x inverse dot x dot y. So x dot y is defined. So having an inverse, and similarly in the other side, right? So I did things in one way, but I could have used the other one to see that y dot x is also defined. So having an inverse means that you multiply with everything. So a partial monoid, which is somehow groupy, I mean, that's just a group. Okay, so the invertible elements multiply with everybody. Now this isn't quite what's on the next slide. So here's an answer to my initial question about partial groups, which was, are they ever two Segal? And I was really thinking, are they two Segal? And one of the first things we did together was we figured out, well, if you have a partial group and it is two Segal, it still didn't say what a partial group is. Then it's actually a group. So multiplication is totally defined. It does not go via the previous slide, because the previous slide is really telling us that we shouldn't expect partial groups to be partial monoids with sort of inverses, because that would just be a group. So I'll come back to this little theorem at the end. But first, I would like to say what a partial group actually is. And for that, I mean, well, one, I'm going to give my perspective on what a partial group is. So for that, I want to bring in symmetric simplicial sets. So for this, let's talk about the category, which we'll call today upsilon. So this has the exact same objects as a simplicial category delta. So these bracket n's that are the ordered set 0 up through n. But morphisms here, instead of being order preserving functions, I'm just going to take all functions. Right, so this is some kind of enlargement of delta. It's certainly equivalent to the category of non-empty finite sets. It's a skeleton of that. And then a symmetric set, just mimicking a simplicial set. It's a contravariant functor. And we get this functor category sim, which consists of all the symmetric sets. Okay. So these are just simplicial sets with some additional structure. So you have more, this bigger category acting on your graded set. In particular, the symmetric name is coming from the fact that the set xn has an action of the symmetric group on n+1 letters, because that's the automorphism group of bracket n. Okay. So these can go wherever they like. That's exactly sigma n+1. Okay. Now, questions on this slide? Or good so far? Okay. So here's a slide from earlier. This is the theorem of Grothendieck that says that a simplicial set is the nerve of a category if and only if these Segal maps are bijections. And this is a fully faithful subcategory reflective. But let's alter this for symmetric sets. And I think that does it. Now, this changed. So here I've crossed out simplicial and replaced it with symmetric. I've crossed out category, replaced it with groupoid. Theorem is still due to Grothendieck. It's actually this exact same proposition in there. So it's all one theorem actually. Yeah, so this is telling us something about nerves of groupoids. One, nerves of groupoids are symmetric sets. They have this additional action. I want to say something about that. And we can exactly classify nerves of groupoids just as we do for categories.
I have a question.
Yeah.
Yeah. So can you say something about the geometric intuition behind symmetric sets? Like, for instance, I have a one simplex, and I guess the group action, well, there's no group action of x1. Can you reverse the direct, okay, if I have a two simplex.
No, but there is a group action on x1. So this is going to be on the next slide. Because
yeah, okay.
Just sigma 2 would act on
x1.
Yeah,
okay. It's sigma of n. Okay, yeah, okay.
And I'll show you on the next slide my interpretation in this case.
Okay, thanks.
But yeah, great question. I mean, geometrically, if I draw in the simplex, what are these extra symmetric group actions doing? They're permuting the vertices around. And what that's doing is it's also permuting the simplices around when you do that.
Okay. Thanks.
Right. So we have this. So groupoids sits inside of categories. We have that this nerve extends. What else to say? And up here, there's also a reflection. Groupoid is also a reflective subcategory of symmetric sets. But let me say a little bit about why this is good. So, or why you might be brought to this. So the first thing is that bracket 1 has this flip map. So it has a non-trivial automorphism that just flips the two elements, swaps them around. And I'm going to interpret this as, so this gives us a map from x1 to x1 if x is any symmetric set. That sends f, and I'm going to write to f inverse. I should probably justify a little bit about why I'm writing f inverse there. And the explanation is that if you multiply f and f inverse, you get the identity back. So for example, I also have this fold map that starts at bracket 2, goes to bracket 1. 0 goes to 1, 1 goes to 0, 2 goes to 1. So I think about this as sort of folding 2 into 1 that keeps this middle point where it is. And there's another fold map 2 that does the opposite thing. And if I precompose this with precompose with either delta 0, delta 1, or delta 2. Then we can see what happens to this action of this fold map on our symmetric set X. So it sends a 1 simplex here. Actually, if I do delta 2, so skip 2, it flips. So then I get 0 goes to 1, 1 goes to 0. So that's why I get F inverse here. If I precompose with delta 0, so I don't have this part, then I sort of get 0 maps to 0, 1 maps to 1. That's why I have an F here. And if I precompose with delta 1, which skips 1, then I got 0 goes to 1, and 1 goes to 1. And that's why I have an identity here. So this fold 2 simplex is sort of representing that F inverse actually is an inverse. At least in this case, it's a right inverse, but you can do the same thing to see it's a left inverse. Okay. So yeah, so symmetric sets, these are a great home for groupoids. Now it turns out they're also a great home for partial groups. So weakening this just a little bit, what we call a spiny symmetric set. I could give this definition for simplicial sets too. This is one where the Segal map isn't a bijection, as I asked before, but rather it's just a monomorphism. So it's an inclusion. For all n bigger than or equal to 2. And I'm mostly going to ignore this sort of fiber product and just think about the collection of one simplices that make it up. And you know, examples here would of course include groupoids, since that top map is actually a bijection, or groups, but more stuff than just that. And you know, you could also have categories if I'm doing the simplicial set version, or partial monoids. But that's spininess or edginess, if you want. Okay, and now we can actually give a definition slash theorem. And that's that a partial group, it's a spiny symmetric set which is reduced. Meaning that you only have one vertex. So a set of one vertex in X0. Okay, so this is the 1-point set. And I'll say more about why this is definition slash theorem later. And allow me to also write a partial groupoid is a spiny symmetric set. I'm going to treat these as synonyms. Mostly because I'll probably say this, partial groupoid. That's what I mean. I mean exactly spiny symmetric set. So the multi-object version of that. Let's see some examples. First example, of course, groups. These are partial groups. So given any group, I can look at its usual BG, and by this I mean, let's say the simplicial set rather than the associated space, with BG(n) being n product of n copies of G. This is also a symmetric set. This is a very prototypical partial group. Two, something that's not a group. If I have any two groups G and H, I can take their wedge where I identify the identity elements, but don't let myself multiply anything from G and H together. And this happens to sit inside of the sort of free product of G and H. Three, an example that I think you've seen it here before. So you've seen this at least last fall, but maybe much more recently than that as well. And that's BCOM-G. So this is a subsymmetric set of a BG consisting of those words of length n, where each element of G or each element commutes with every other. In other words, those lists that are supposed to generate abelian subgroups of G. And actually, these two examples are both sort of symmetric subsets of some BG. Any symmetric subset of a BG is automatically going to have this spininess property. Still, maybe I should add something maybe I should add non-empty. Because I do want Z0 to be a point as well. That's a pretty big class. Another example is if I take a groupoid. This is something you might think of as kind of like a partial group because I can multiply, or I can compose some elements with some others, but I can't multiply everything. This is again determines a spiny symmetric set. I can take G and think about it as a symmetric set itself. And then I can quotient out by all the zero simplices, identify all of those. I have to do it in every simplicial degree if I have one of those zero simplices and a degeneracy of it. So explicitly, the n simplices here are sort of the n simplices of G, where not all of the GIs are identities, and then you have a single guy that represents all of the identities in all of them. So this is no longer a groupoid, or it's no longer a group, but it is a partial group. Questions?
Sorry, the fifth example, couldn't get it. So these simplices are not all. Oh, I see. It's just what is the motivation for that object? So the G bar, yes, or some, yeah.
Yeah, G bar. So what I mean, what is the motivation? Well, some definitions of groupoid are given by not specifying any objects, and instead saying, well, if you've I have some multiplications of my elements defined, but not all of them. And if I have some, I can, get some kind of associativity out of this. So like a groupoid, if I forget about the objects and just thinking about the compositions, it is something like a group with a partially defined composition operation. This is a way to make it precise why it's a partial group, this particular notion. I'm not sure if that answers the question, but
Okay, so for this to make sense, you need multiple objects, right? For single objects, this is not really.
Yeah, if I started with a single object groupoid, then I haven't changed anything.
Yeah, okay.
So single object groupoid, this is just exactly the group I started with, or exactly the BG I started with. But for a multi-object one, this is actually doing something.
Mhm.
And, you know, also, I mean, you can recover, I can recover G from this. At least up to components that don't have any non-trivial morphisms.
Mhm.
So those get to all, I mean, those become invisible, right? If I have a component sitting out there with only an identity morphism, well, I can't tell that I ever had that or not. But otherwise, I can recover the original groupoid.
Okay, thanks. So one more question. So for in number 4, are there any other interesting sets that are outside the class 1, 2, 3? Like subsets, symmetric subsets are interesting, but not say. I mean, we know like commutative classifying space. There's this version where you can include this some sort of like torsion condition, but not very. I mean, something very different than these. I should say maybe.
Yeah. So I think in 2 slides, I'm going to give. I think many examples that are very interesting fall into point 4. Besides these, and I'll give at least an indication of some.
Okay, I can wait.
Yeah, no, but the answer is yes, there are lots of interesting ones. But even here, this BCOM G is like the first in a series of sort of nilpotence class of
Oh,
things.
that's also right. Yeah. So there's also that
So this,
sequence of subgroups. Yeah, it's subspace. Yeah, you're right.
yeah, so
Okay, so I think I automatically thought maybe not those. Okay, yeah, okay. So my question was not clear enough, but yeah. So there are variations of the commutative classifying space. Yeah, the
yes,
detorsion version or higher nilpotence. You might have, you can define using p-adic groups and so on. Yeah. So there are versions
yeah.
of that, but I was thinking maybe something very different than.
I'm going to
But
give something very different as well.
Oh, okay. Maybe not
So
coming from commutation, that's what I should say.
yeah. So there are definitely variations of this, but I'll give more for 4 in a minute.
So,
Uh,
sorry, could I just ask? I'm trying to understand the. I'm just trying to get my head around the 5th point. So this is. Are you making the claim that this is actually what a partial group is, or this is equivalent to the definition of a partial group? Any gadget of this form, or that we should be thinking about partial groups as being?
You should not. So no partial groups come from groupoids in this way.
Okay.
It's a sort of very special condition.
Okay.
So this is a very special class.
Okay. Thanks.
In 5. Right. Most do not come from this at all. I have a characterization somewhere of what these are, but like it's super special.
Okay. Thanks.
So another example, before we get to maybe the more interesting classes. Well, this one's a partial groupoid. So look at the representable functor on bracket n. This is the nerve of a groupoid, namely the chaotic groupoid, where if I give you 2 objects, there's exactly one morphism from one to the other. So sort of take the complete graph. So this is definitely a partial groupoid because it's a groupoid. And if I reduce this, then I get a partial group. This should be considered a free partial group on a composable word of length n. And surprisingly, this is not a partial group that appeared in the literature before. And what does it do? It classifies exactly sort of length and composable words in your partial group, because maps out of it, well, it's the same as maps out of of symmetric sets out of this upsilon n, because of course every vertex here has to map to the unique vertex of x. So I haven't lost any information by doing that. But that's just exactly xn. Okay? So an xn is the set of composable words in your partial group. So in general, this hadn't been seen, although I guess F1, which is the free partial group on a single generator, that's been known since the very beginning. So that's has words that look like this. So I'm not allowed to multiply A with A, because that's not some partial groups I can't do that. I have an element that doesn't multiply with itself. For example, in the reduction of a groupoid, I might have a morphism that I can't multiply with itself because its source and target are different. So it just really has words that sort of alternate between A and A inverse, maybe with some identities thrown in the middle. So it's nice to have this around, because then you can sort of do kind of co-representable arguments or something. So this 7 is my answer about other nice subsets of BG. So if I have G acting on a set Z, so just a group G, I can form this this action groupoid. So I can get a groupoid E living over BG. I guess all of this is in symmetric sets. So this has like vertices Z, and then morphisms G from little z to GZ. Or this is taking the sort of a standard discrete op vibration associated to this group action, and then taking the nerve or something. So we can always do this. But now if I take any subset of Y, then I can form Y prime or E prime. And this still lives over BG. So this has E prime 0 is Y, which sits inside Z, which is E0. So I'm just restricting the set of objects, still the nerve of a groupoid, taking the full subgroupoid or something. And I'm going to let, and I'm going to look at its image. Okay, so the image of E prime within BG. So this is some symmetric subset. We're going to call it, I'm going to call it today Ly of G. So this has n simplices. Those n simplices in BG, so strings G1 up to Gn, so that there exists, I mean, this is a groupoid, but I've forgotten how I got this. So there exists a Y0 up to Yn in Y, so that Gi, well, it acts on Yi minus 1. That, I mean, this is a kind of a partial action of G on Y. So that may just be some element of Z rather than a Y itself. But I want that to be the next element of the sequence. Okay. So this is sort of a subtle thing. But actually, many of the most important examples are turn out to be of this form. So sort of the image of this partial action groupoid or something. So actually the motivating special case from the group theory side is of this form. So there they take the set that gets acted upon are non-trivial P subgroups acted upon by conjugation by a group. And you start with a CeLO P subgroup S, and then Y is like the non-trivial P subgroups of Z, which live inside of S. Okay. So certainly I could conjugate one of those and end out outside of my CeLO P subgroup. So a conjugate of a subgroup of even a conjugate of S, maybe just some other CeLO P subgroup. So it can go outside. And in this case, this is maybe the real case. This is where all the group theory comes, is here. Now I'm not a group theorist, so I'm not going to say too much more about this. But this is a very special kind of partial group called a locality. And I want to end the examples with this one, which is actually going to tell us that not everything is of form 4. Not everything is the symmetric subset of BG. So there is a partial groupoid with elements like this. So that's sort of both ways of multiplying are defined, but they're not equal. So a kind of non-associativity. And this is just done by sort of construction. So you can do this with kind of gluing constructions with these upsilon 2s. So I could say, well, maybe I want to be able to compose G1 and H1, get something here, and then I want to compose F1 with this, glue to get a B, and then do it the other way, and then glue together these G's and these F's and these G's and these H's. And so the claim is that this D is the partial groupoid that sort of satisfies this. There's no reason. If you do this right, you can see that you're not going to have K1 and K2 giving the same one simplex in D. But this is a little subtle, right? Because I'm writing down a push-out diagram. Where does this push-out live? Does it live in symmetric sets? Does it live in partial groups? How do I know that K1 and K2 are different? But I'll say a bit more about this. First, I want to say a little bit about this definition / theorem, which said that a spiny symmetric set, a spiny symmetric set is one where this map is injective, and then a partial group was a reduced spiny symmetric set. So why definition theorem? Andy Chermak did all the initial work, invented partial groups in this form, but with a sort of very hands-on definition where you had explicitly defined partial products from the set of words in your set, along with an inversion operation, and then you've satisfied a bunch of axioms. Gonzalez proved that this data could actually be encoded in simplicial sets. So he showed that in our language that these partial groups are reduced spiny simplicial sets, not symmetric, together with an involution function, which is something from Z to Z up, so that if you have some n simplex in Zn, then I can form this other bigger n simplex in Z2n, whose multiplication should specify that. I want this inverse to actually be an inverse. Well, with total multiplication E. And at the beginning, I spent a lot of time wondering about this theorem, and why, is this extra structure? Turns out this is not extra structure. This is sort of forced as it is for groups. You don't have any choice about your inverses. And so what Justin and I did was we gave this sort of one-line definition. Once we have symmetric sets at hand. But it very much builds on this Gonzalez characterization. And I'm not going to say too much about how this is proved, but the main ingredients are understanding a special set of generators for this category upsilon, and as well as like getting a sort of matrix for the elements. Now, maybe I don't really want to say much about these generators, but it turns out you can generate upsilon with the order preserving maps that are already in delta, along with these folds. But I'm going to leave this for now. So these folds are very much related to the extra elements you get in Gonzalez's theorem. Do we go for 50 minutes or 1 hour?
1 hour is fine if you
1 hour is
want.
fine.
Yeah.
Sure. I think we should say something about higher Segal stuff since we started there. But maybe just before, I'll just briefly say that this partial groupoids, this turns out to be a reflective subcategory of symmetric sets. So there's left adjoints here. Likewise, there's left adjoints here. And I guess there's also left adjoints here and here. And sort of the diagram with all those left adjoints also commutes, which is unusual. And this implies by sort of formal stuff that partial groups or partial groupoids is actually a bicomplete category. It has all limits and colimits. Limits is not so bad. It just means that these are closed under limits because the inclusion is a right adjoint, so it preserves limits. But this gives us a good way to compute colimits. So you first compute the colimit in sim. So if I have some diagram landing, let's say in partial groupoids, I can compute the colimit up here. That can easily take you out of spiny symmetric sets. Right? This often happens. Sometimes it doesn't, which is great. But then I apply the reflector to get back to a partial groupoid, and that thing will turn out to be my colimit. So if you get a good handle on what the reflector is, you might actually be able to use that to compute something. Better is when I take the colimit here and I haven't left spiny symmetric sets. Then I don't have to actually reflect. But this, this was the limits condition was proved by Chermak, and then Salati's paper actually proves that you have all colimits. They do it by very different means. And me as a category theorist, I had a hard time understanding this. But this gives me this is how I like to understand it, is by these reflections. Here's a bit about how the reflections go. Let's not say anything about this. You can prove this very abstractly if you want, but you can also give a hands-on description of the reflection. But I prefer to talk about Segal spaces. Is that okay? Or does anybody really want to know about the reflection? I don't think we want to know about the reflection. Okay, so I'll say a little bit about higher Segal spaces, and I'm not going to say too much. But I did definitely want to address this theorem that any two Segal partial group is a group. And maybe the better theorem is this one, which doesn't say anything about spininess. There's no spiny here. So this isn't about even more general than partial groupoids. Then the theorem says that X is upper 2 Segal if and only if it is actually Segal. So that is, Segal means it's the nerve of a category or isomorphic to the nerve of a category. And the whole idea is that because you're working in a symmetric set, you can permute elements around. And you might have, I know I'm not saying too much about higher Segal conditions in this talk, but you may remember I drew a square like this earlier. So this is something about one of the faces, or one of the outer face interface pull things or pullbacks. And actually, these two squares become isomorphic because in the bracket n+1, I can permute the elements i+1 and n+1 and maybe move things around a little bit. And that's it. So one of them is going to be a pullback if and only if the other one is. Now, this doesn't cover everything because there's still sort of this bottom dimension where I don't have any upper 2 Segal squares. But then this becomes a sort of retract argument. And so this bottom layer is a retract of the one layer up. So this is just a very brief sketch, and this works much more generally. So this would work for X is upper 2K Segal if and only if it is lower 2K minus 1 Segal. But that's why this holds. And so we know partial groups are not 2 Segal, but some of them are higher Segal. So this is my last slide. And it just says that here are a couple partial groups that we saw today, which are lower 3 Segal. So if I take a groupoid and I reduce it, well, if the groupoid was actually a group, then this is still 1 Segal because I didn't do anything. But if not, it's lower 3 Segal. And also BCOM G, that's always lower 3 Segal. Now I'm not here to tell you what lower 3 Segal is. That's a big task. But the idea is you have sort of cubes like this that you want to be Cartesian. And this ends up being just a sort of check. So if I had some list of elements in G and I wanted, I had what should be their faces under these maps, D0, D2, D4, in a just world, we'd end up with like X, Y, Z if I do D0, and D2 is going to multiply in the middle. But I don't actually have an element here that I'm doing this with. So that I'm proposing that I do have an element, and you just have to see that everything commutes with everything else. And you can just read that off of the fact that these are 3 simplices here. But I think that's a good place to stop.
Okay, thank you. Any questions for Philip?
I have one question. Sorry, Philip. Are there isomorphism theorems for partial groups, like for actual groups?
I don't know. That's a great question. Yeah, no, I do not know.
Okay, thanks.
Can
I
I?
guess they need more structure because I guess there are such results for localities, but they need this structure.
Thank you. Other questions?
So I have one about your last slide.
Does this slide?
Yes. What do you mean by thank you? No. So like the only algebraic or non-geometric intuition I have for higher Segal things, like the upper and lower k-1 Segal things, is this paper of Gall and Gall that's like n-dimensional lax associators becoming vertical, which I've always had some trouble parsing. Did proving this result give you some intuition for what, say, the lower three Segal condition means algebraically? Like, can you convey in some way something that isn't the lax associator becoming an actual associator?
So I don't really, I don't know too much about the Gull and Gull paper. And yeah, and so I don't know. So I don't necessarily know what this means. I'm just like sort of following Tashi's work and learning how to check the thing. So maybe that's not satisfying, but yeah, I don't know.
I mean, it's as satisfying as anything I can say about it. But
yeah, I'd really like to know about sort of this algebraic structure and how that works.
if you were following Tashi's work, do you have like an excisiveness explanation for this, or?
So no, everything is I mean, everything we're doing is just looking at the particular Cartesian cubes that we have to look at.
Okay.
Right. So it's all for me. I mean, I guess you're aware that I come from the decomposition space side of things, so everything is calculus of pullback squares. Here, everything for me is calculus of Cartesian cubes.
Okay.
Which that's all I think about it in terms of this.
Okay. There's seems to be another question by Victor on the chat. Okay, so maybe I can ask this question. Is there a nice concrete notion for a quotient partial group? But okay, was this covered in the previous question or is it? No.
Yes, they exist because of the category is closed. So yeah, the quotient is a colimit, but I don't know if it's easy to describe the quotient of partial groups.
Yeah, so these do exist. And you have to be careful about what you mean. So I would say yeah, I guess the question is like quotient by what, right?
By a normal partial subgroup or something like that. Yes.
Yeah, so the question is really, quotient by what. And so these quotients do exist. Salati's paper, I think, talks a lot about this. About which ones these are and how to get at them. Me as a non-group theorist, I think more about things like building partial groups from generators and relations, something like this. And that's a sort of quotient partial group as well, but maybe not quite what you're meaning. But so the answer is yes.
Oh, good. Yes. Thank you, Philip.
Sure.
I also have a
So I
question.
have,
Okay, so there's a
Oh.
question, right? Okay, you can go ahead.
okay, me first. Yeah, so on this notion of symmetric set, yeah, I thought it wasn't, so, could you maybe say just in words, so can a groupoid be said to be a symmetric set such that from, what, I mean, is there, so you were saying like groupoids fit inside symmetric sets? So what, and you say what, like a Segal condition or a horn or what?
Yeah, sure. Here's one method of doing this. So within, I guess I've switched to black. So inside of upsilon n, there's a sort of spine. And I'm drawing this one way. Right, so I start here and then I pick out exactly a spine like this. Or I start with this guy and I pick out sort of this spine. And what we ask is that you're kind of orthogonal to this. For all n. So this is a manifestation of the Segal condition. And so is this the sort of thing you're looking at? So these are Segal.
Yeah, I
symmetric.
mean, I'm just thinking if there is a more natural way to think about infinity groupoids with symmetric sets rather than with simplicial sets.
Yeah. So
you put Segal condition. Oh, sorry.
Szynski has a model structure
Yeah.
modeling infinity groupoids using symmetric sets.
So this, I mean, we actually took upsilon from Szynski. Lots of people use different things, but has a model structure. So absolutely. So I didn't talk about this, but for infinity groupoids. But yes, you absolutely can do this.
Okay, great. I was unaware. So thanks.
Yeah. And I should say something else. I'm sort of looking at these spines here. But there's actually lots of choices I could be making instead of this one. So this is sort of a graph that's like linear in there, but I could have taken a kind of star-shaped graph, or I could have taken all kinds of other things. So I just really need to pick a spanning tree for the complete graph on n+1 elements. It doesn't really matter what
Just
spanning tree I take.
one last out of curiosity remark. So is it okay to think of symmetric sets as sort of simplicial sets without orientation, or that's wrong? Like
With what?
symmetric, is it okay to think about symmetric sets as simplicial sets without orientation somehow? 'Cause-
That's how I'm often thinking of them.
Okay, thank you. Thanks.
Okay, so I also have a question. So the last slide again before thank you slide, this one, yes. So the commutation relation, I mean, one can just look at extension conditions or some conditions that give you that is satisfied by BCom, and at the end of the day, I suppose it would boil down to checking some commutation relations, right? Or implications of certain commutations to other commutation relations. That's the case here. So do you know if this condition here is a complicated, non-trivial one, so to say, that people who work on these important groups or some sort of commutation calculus, I suppose, would be shocked.
I'm not sure about this result for the nilpotence thing.
No, I mean just commutation I mean, you have this very basic statement on the right-hand side, I think, which amounts to, if I haven't understood it wrong, it amounts to the lowest 3 Segal condition in terms of commutations, right? Commutation relations. So this commutation relation, I mean, you might end up with something very trivial, right? That is, very basic relations, just, implied by very basic relations of commutator, right? But the condition here, it looks non-trivial, but how non-trivial is it? That was my question. So is it
so you mean the condition on the left?
on the right?
On the right. I mean, I think this is to me, this is very trivial. So
Oh.
I don't know the answer, but I mean, I think this is I don't think there's anything subtle or anything going on.
Okay, so we can say that the BCom satisfying being a lower 3 Segal is not very deep about the commutation relations.
I do not think it's very deep.
Oh, okay, that's what I wanted to ask. Okay, thank you.
But it is an example, so I think that's
Okay, I see. Okay, so Victor seems to
Can
have
I
another
also ask-
question. Okay, sure, yeah,
Can I
maybe
also
Admin
ask a
should ask that.
question? Is that okay? So for one of the motivations when Chermak defined the partial groups, it was sort of a model for linking systems, a category. So these localities correspond to these linking systems, which are categories. Is there a similar correspondence in the examples you gave with G sets and maybe other examples of partial groups? Is there something similar to ranking system which you can associate as a category?
I don't know.
Or like what conditions will make this such a sort of
Yeah.
construction possible?
The thing is that this yeah, like this locality stuff is sort of still very mysterious to me. Like it's very subtle. And yeah, so I don't know. But yeah. I would guess that in general, you're not gonna be able to do anything like this, right? If their partial groups are too wild. I mean, I think localities are super special.
Thank you.
I see there are other questions on chat. So it would be nice a result kind of when the nerve of a, oh, okay. So I think Victor has a question asking when the nerve of a, or maybe when is a partial group, a K-pi1 space. So
It was
what's
just a
K-pi?
comment, yeah.
Yeah, okay, I don't know. That's not a question. So the other question is, does this perspective help give a notion of morphism between localities, especially arising from morphisms of underlying fusion systems? So it's Matthew's question.
I don't know. So these sort of morphisms that you're talking about between fusion systems are very complicated. I know Justin would really like to know the answer to this. But right now I don't.
Okay, any other questions for Philip? So if not, let's thank Philip. Okay, thank you, Philip.